So today we're talking about something called Alchemy 2.0.
Mm.
And no, before you start thinking about transmutation circles or turning lead into gold, that's not what this is.
Not quite.
We're talking about how modern science is designing, say, harder diamonds or more effective drugs, not by trial and error in a lab, but by solving equations on a computer.
It's a fundamental shift, really, from
Hmm.
discovery by accident to discovery by design. And the tool for this isn't some philosopher's stone.
It's quantum physics.
It is, specifically, a field called ab initio electronic structure calculation.
Ab initio, that's Latin, isn't it?
It is. It means from the beginning, or from first principles. The whole idea is that you're not relying on experimental data to get started.
You're not cheating by looking at the answer key.
Exactly. You're calculating how matter should behave starting from the fundamental laws of physics and nothing else.
And to guide us through this, we have two really interesting sources. First, a theoretical overview by Dr. Mohammed Abdur-Rashid on something called density functional theory, DFT.
Right. And to balance that out, we have a really practical, almost boot camp style book by Rio Maizono called Ab Initio Calculation Tutorial.
It's a great pairing. Rashid gives us the why, the beautiful, complex math behind it all.
And Maizono gives us the how. He
Yeah.
literally walks you through running these quantum simulations on a completely standard computer.
See, that's the part that really got me. I always associate quantum mechanics with, like, supercomputers, liquid nitrogen.
Massive server farms.
Yeah. But Maizono's argument is that you can basically do this at your kitchen table.
You absolutely can. But before we get to the hardware, we have to talk about the theoretical impossible. We have to understand why this was considered for so long to be completely unsolvable.
And that all starts with the Schrödinger equation.
The famous one, h pi I equals E psi.
Right. And in theory, that equation describes the behavior of everything at the atomic level.
Everything. If you solve it, you know the energy of your system, you know where the electrons are, you know how it'll react. You basically know everything there is to know about that piece of matter.
So if we have the master equation, why the need for this Alchemy 2.0? Why not just solve it?
Because of something called the many-body problem.
Which sounds like a great title for a sci-fi novel.
It does, doesn't it? But really, it's a mathematical nightmare. I mean, think about a single hydrogen atom, one proton, one electron.
Okay.
That's a two-body problem. We can solve that with pen and paper. It's actually quite elegant. But what happens when you add just one more electron? Or you think about a crystal of silicon with, billions of electrons.
Oh, right. Suddenly everything is interacting with everything else.
Precisely. Every single electron repels every other electron. The nuclei are attracting all the electrons. It's this incredibly dense web of interactions.
Yeah.
And mathematically, the complexity just explodes. The wave function, that Greek letter psi, it depends on the position of every single particle.
Okay, let's break that down. If I have, say, 100 electrons, how many variables are we talking about?
Well, each electron has an x, y, and z coordinate. So for n electrons, you have 3 n variables.
So 300 variables for just 100 electrons.
And for a real material, a mole of silicon, you're looking at something like 10 to the 23rd electrons. The equation becomes a function of, a number of variables so big you can't even write it down. It is completely analytically unsolvable.
So for decades, physicists were just stuck.
They were stuck making compromises, approximations. And the first big one is the Born-Oppenheimer approximation.
Which sounds incredibly complicated, but the idea is actually pretty intuitive.
It is. It just comes down to mass. Nuclei are thousands of times heavier than electrons, so they move much, much slower.
So you just pretend they're not moving.
You essentially freeze them. You pretend the heavy atomic nuclei are stuck in cement, and you only calculate the paths of the light, fast electrons buzzing around them.
Okay, so that helps. You freeze the background.
It helps, but you still have all those electrons interacting with each other. It's still a mess. And that is where the genius of Walter Kohn comes into the picture.
Yeah.
This is the birth of density functional theory, or DFT.
This is the big hack. The one that won the Nobel Prize.
It's a brilliant, brilliant conceptual shift. Kohn and his collaborator Hohenberg, they proved these two theorems that just changed everything. They showed that you don't actually need that ridiculously complex wave function to know everything about the system.
You don't need the 3n variables.
No. They proved that all you actually need is the electron density, a function called n of r. It's just the probability of finding an electron at any given point in space.
Wait, hang on. Explain why that's so much easier.
Okay, think about the variables again. The wave function has potentially millions or billions of them. The electron density, it's a function of just 3 variables.
X, Y, and Z.
That's it. It doesn't matter if you have 10 electrons or 10 billion, the density is always just a simple 3D map.
That is an unbelievable compression of information. You're trading a million-dimensional problem for a 3D map.
Exactly. And the Hohenberg-Kohn theorems prove that this map is unique. If you know the ground state electron density, you know everything. The density uniquely determines the energy.
Okay, there has to be a catch. If it was that simple, we would have solved material science in the 1960s.
There is a catch, a big one.
Right.
While we know the density determines the energy, we don't know the exact formula, the exact functional, to get from one to the other.
So we know the treasure chest exists, but we don't have the map to find it.
A perfect analogy. So Kohn and another physicist, Sham, they came up with a second trick. They mapped the messy, real system of interacting electrons onto a fictitious system.
A fake one.
A fake one.
Yeah.
A system of non-interacting particles that just happens to have the exact same electron density as the real one.
Okay, so we're simulating something that doesn't exist to understand something that does.
Yes, because in this fake system, the math is easy. The particles don't interact. We can calculate their kinetic energy perfectly. The only part we don't know, the part with all the messy quantum weirdness, we just shove it all into a single term.
The exchange correlation potential.
The famous VXC.
I love this. It's like cleaning your house by shoving everything you don't know what to do with into a junk drawer.
It is exactly the junk drawer of the equation. We calculate the easy stuff precisely and then say everything else. It goes in the junk drawer. And the amazing thing is that even really simple approximations for what's in that junk drawer work surprisingly well.
So we've gone from impossible to solvable. Now let's pivot to Maisonneau's book, because having the theory is one thing, but sitting down at a computer and actually doing it is something else entirely.
And Maisonneau starts with this really important warning. He calls it the beginner's disappointment.
I really related to this. You download this super sophisticated software, he uses quantum espresso in the book, and you expect to see, I don't know, a movie of atoms bonding.
Or a big flashing sign that says, this is a superconductor.
Yeah. And instead you get a text file full of numbers. The software, the kernel, it only gives you two main things: the total ground state energy and the charge density. That's it.
No movies, no melting point.
And that's where people quit. They think it's broken.
Right. But Maisonneau explains that this software is like a black box that answers one and only one very specific question. If I put atoms in this exact arrangement, what is the total energy of the system?
So how do you get to the cool stuff? The conductivity, the elasticity?
You have to use what he calls the outer loop. And this really is the core skill. You have to design a whole series of calculations to poke and prod this system.
Okay, walk me through an example. Let's say I want to know if a material expands when it gets hot. Thermal expansion. How do I get from just energy to that?
Okay, so first you run the calculation with the atoms at the normal distance.
Yeah.
You get an energy value, write it down.
Step one.
Then you change the input file. You move the atoms slightly further apart to simulate a larger volume. You run the whole calculation again, get the new energy.
So you do this over and over for different volumes.
You do. You're basically mapping out the energy landscape. You get a series of points and you fit a curve to them. The steepness of that curve tells you how the atoms vibrate, the phonon frequency. And from that, you can use a standard physics formula to calculate the thermal expansion.
Wow. So the simulation isn't the answer, it's just the data generator for your model.
That's it, exactly. Maisonneau calls this psi-zero modeling. It's the art of taking a real-world problem and translating it into a set of simple questions that the ab initio code can actually answer.
That really feels like the alchemy part. You have to be clever about the questions you ask the computer.
And you have to know how the computer thinks. I mean, it doesn't even know what temperature is. It calculates everything at absolute zero. It's up to you to build the real world on top of that ground state.
Maisonneau has a really great analogy for the workflow. He talks about making bread.
Yes, the dough analogy. This is so important for understanding what the computer is doing while you're just staring at a blinking cursor.
So he says the first step, the self-consistent field calculation, or SCF, is like making the dough.
Right. Remember how the potential depends on the density, but the density depends on the potential.
The chicken and egg problem.
Yes. So the computer has to start somewhere. It just guesses. It says, okay, let's assume the density looks roughly like this. It calculates a potential from that guess, solves the equations, and gets a new density.
Which is probably wrong.
It's definitely not the same as the first guess. So it mixes the old one and the new one and tries again and again and again. It iterates until the input density and the output density are basically identical.
It's converged.
Your dough is fully kneaded. It's ready.
And baking the bread is the next step, the electronic structure part.
Exactly. Once you have that converged density, the perfect dough, then you can calculate things like the band structure, which tells you if it's a metal or an insulator. But his point is so critical. You cannot bake fancy bread with half-finished dough.
If your SCF calculation doesn't converge, all your results are just garbage.
Complete garbage. Garbage in, garbage out. It applies to quantum physics just as much as an Excel spreadsheet.
Okay, so let's get practical. What do I, the user, actually have to feed this thing? What are the inputs?
You really only provide two main things. First, the geometry. You have to tell it where the atoms are.
And you don't just make this up.
No. Usually you get what's called a CIF file, a crystallographic information file, from an online database. You can download the exact experimentally determined structure of quartz, for instance.
So I tell the computer, put a silicon atom here, an oxygen atom there.
Precisely. The second input is a bit trickier. It's the pseudo-potentials.
That sounds like a fake superpower.
It's a very clever computational trick. Think about a heavy atom. The electrons way down deep inside, close to the nucleus. They don't really do much chemistry. They're just there,
Yeah.
tightly bound.
So simulating them is a huge waste of time and energy.
A massive waste. So what we do is we replace the nucleus and all those core electrons with a pseudo-potential. It's a smoothed-out, effective potential that mimics the effect of the core on the important outer electrons without having to calculate the core itself.
It's like blurring out the background in a photo to make the main subject sharper.
That's a great way to put it. But choosing the right pseudo-potential is crucial. If you pick a bad one, your simulation will not match reality.
And in his tutorial, Maisono has you do this for silicon dioxide, SiO2.
Yes, he has you compare the energy of different forms of it, alpha quartz, beta quartz, cristobalite, and this really highlights one of the key strengths of these methods. The goal isn't always to get the absolute energy of the universe right, it's to compare things.
We're looking for trends.
Exactly. Is structure A more stable than structure B? Does the energy go up or down when I squeeze it? That relative accuracy is where DFT really shines. The absolute energy might be a little bit off, but the difference in energy between two configurations will be very, very accurate.
Now, this is where it gets really mind-blowing for me. I think of this work happening in a university supercomputing center. Maisono says you can do all this on a Raspberry Pi.
This is the democratization part,
Yeah.
a Raspberry Pi 4 Model B. He says it cost about $130 for the whole setup when he wrote the book.
A tiny computer the size of a credit card?
And it can solve the Schrodinger equation. I mean, it runs Linux, just like the supercomputers do. You can install open source software like Quantum Espresso right on it. His whole point is that the barrier to entry isn't money anymore, it's knowledge.
That is just wild. You could be simulating new materials in your living room.
Now, to be fair, it's slow. You're not going to simulate a giant protein folding in real time. But for learning, for simulating a simple crystal, it works perfectly. And it teaches you the logic just as well as a multi-million-dollar machine.
And this combination, cheap hardware, powerful software, it leads to the bigger picture he talks about, the materials genome.
This is the future of the entire field. Think about the Human Genome Project. We mapped human DNA to understand biology. The materials genome is about mapping the properties of every possible combination of elements.
But there must be, infinite combinations.
There are. And that's why we need what's called high-throughput computing. This is where you automate that outer loop we talked about. You write scripts that automatically generate thousands of crystal structures, run the calculation for each one, and store the result in a database.
So instead of a person typing things in, a script just tries every possible arrangement.
It does. It builds a massive library of matter.
And
then you unleash AI on that library.
Data science.
Yes. The AI can look through this massive database and spot patterns a human could never see. It might say, based on these 10,000 results, if you combine lithium and cobalt in this specific way, it should have double the battery capacity.
Even if no one has ever made it before.
Even if it's never existed on Earth, the simulation predicts it. And then the experimental scientists can go into the lab and try to make that one specific promising candidate instead of trying thousands of random things.
It completely flips the scientific method. You simulate first and then you verify in the lab.
It accelerates discovery at an exponential rate. And Maisono points out this is a huge opportunity for what he calls latecomers.
What does he mean by that?
Well, the classic community, the physicists who developed all this stuff in the 60s and 70s, they were obsessed with the deep math, improving the theory, fixing the junk drawer.
Right.
But a lot of that foundational work is done. The frontier now isn't in writing the code, it's in the application.
It's the size zero modeling. Back again.
Exactly. The real opportunity now is for people who can look at a practical problem, like a cracking phone screen, and figure out how to translate that into a set of calculations the black box can solve. You don't have to be a quantum mechanic anymore. You have to be a quantum architect.
I like that. You don't need to know how to build the engine to drive the car.
But you do need to know where you're driving. You need to understand the limitations, for sure. But you don't have to rederive the Kohn-Sham equations from scratch every morning.
Okay, so let's recap. We started with the unsolvable many-body problem, this mathematical nightmare.
We used DFT to tame it by focusing on electron density, turning millions of variables into just 3.
We learned that the software just gives us the basic energy, and we have to build these outer loops to calculate anything useful.
And we talked about making the dough, that iterative SCF process to get a converged result.
And finally, that all this power is now available to basically anyone with $100 and the curiosity to learn.
It's incredible. It really makes you look at the world differently. Every single object around you is just a collection of atoms and electrons, all finding the minimum energy solution to these equations.
So here's my final thought for you and for everyone listening. Maizono's book really hammers this idea of predicting trends. If we're building these massive databases and AI is predicting new materials and we can do it on cheap hardware, are we getting close to a time where physical experiments are only needed to verify what a computer has already discovered?
That is the provocative thought, isn't it? I mean, in fields like aerodynamics, we already trust the simulation more than the wind tunnel sometimes. Material science is heading in that direction.
A world where we discover the impossible on a silicon chip before we ever hold it in our hands.
And where the lab becomes the validation step for the server. It's a total paradigm shift.
Alchemy 2.0, indeed. Thanks for unpacking all this. It's a dense topic, but I feel like my own understanding has converged a little.
Happy to help bake the bread.
Thanks for listening to The Deep Dive. If you do end up turning your spare Raspberry Pi into a quantum physics lab, let us know how it goes. Until next time.